denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over denominator squared.
Okay, so I've got denominator squared. Derivative of the numerator is this, which is just K1 E1 KI EI over RT squared. This is KI. Minus the numerator times the derivative of the denominator. And we set that equal to 0. So the derivative of the numerator times the denominator plus the numerator times the derivative of the denominator. So the first thing we can do is set it equal to 0, so I can cancel this. And I can also cancel an RT squared at every term. And now I can notice I have a K1 squared E1 minus a K1 squared E1. So I can cancel this term and this term. Now let's see what I have left. So I'm going to take this on the left side of the equation, this on the right. So I've got K1, K2, E1, E1, plus K1, K3, E1 is equal to K1, K2, E2, plus K1, K3, E3. Okay, so I'm going to bring, let's see. Oh, and actually, I could cancel K1 from both sides of the equation. So I don't need all these K1s. So I cancel K1 on both sides. Okay, so let's notice that I can bring this to the left and this to the right. So I have K3. Let's see which one's bigger. Now I want to do it the other way around. Bring this to the right and this to the left. So I've got K2 times E1 minus E2 is equal to K3, E3 minus E1. And I did that in that one way because E3 is bigger than E1 and E1 is bigger than E2. Okay, so I have K2 over K3 is equal to E1 minus E2 over E3 minus E1. And this is K2 0 over K3 0 e to the minus E2 minus E3 over K2.
Should be K3 should be E3 minus E1 over E2 minus E1.
Everyone's talking at once, so I can't hear.
So K2 over K3 should be E3 minus E1 over E1 minus
K2
E2.
over K3, yeah, the other way around. Okay, so I can multiply this out. So and take the logarithm. So well, let's do one step at a time. I multiply out e to the minus E2 minus E3 over KT is equal to K3 0 E3 minus E1 over K2 0 E1 minus E2. I take the log of both sides. And I get 1 over T is equal to K over E3 minus E2 log K3 0 over K2 0 E3 minus E1 over E1 minus E2. And this is, of course, the best T. So we find there's a compromise T that gives me the best phi, and it's not the highest T, it's not the lowest T, it's somewhere in between that I get from, and it clearly depends on the activation energies, as it should.
Is it the K on top should have been an R?
That's an R.
Yes.
It's an R, the argument gas constant.
Gotcha.
Okay, so why don't we do, so let's look at a more complicated situation. Let's say I have A goes to RST with side products. And let's say what I wanted was T. And I have some combination, say E1 greater than E4, E5 greater than E2, and E3 greater than E6. So this reaction has a higher activation energy than this one. This has a lower activation energy than this, and this is a higher activation energy than that. If I'm interested in getting T with as little side products as possible, then I could try to get some compromise temperature. If the temperature is too hot, I'll end up with lots of V. If it's too cold, I'll end up with lots of U. So there might be some compromise temperature, which I would get by trying to write phi T. Say phi T over A, for example. Or what I might imagine is I might try to do some sort of temperature progression, where I didn't take, here I looked at a single temperature and a single CSTR. If I had multiple CSTRs or a plug flow reactor, then I could imagine I'd have some sort of temperature progression. What do you think that temperature progression might look like? Well, I'm sorry?
Since E1 is greater than E4, if you favor E, so lower temperature,
Lower from what?
increase the temperature.
From what? Before I increase something, I need to know where to start.
We first increase the temperature because we want
Increase from what?
from
Input.
A to R. Because E1 is greater than E4.
We
I mean,
start
E2.
increasing temperature. Before I increase something, I need to know where to start.
See,
If I want to improve my grade, I need to know what grade I started with.
You want to start with a high temperature to favor it going to R, and then you want to lower the temperature to favor it going to S, and then you want to raise the temperature again to get it to T.
So I would want to start with a high temperature, look to get R, favor R over U, and then go to a lower temperature to favor S over V, and then go back to a higher temperature to favor T over W. Now, of course, all these reactions are going on simultaneously, so it's not clear how high the temperature should be at the beginning, how low it should be here, how high it should be there, and that's a matter of calculation. That's not a trivial problem. Okay, let's look at another case where we look at the second question, so where separation is expensive. Let's look at a situation, A goes to R, and A goes to S. So in this case, right here where I have E1 is less than E2. So again, I have, if I were only interested in phi, what would I do to the temperature?
Increase it?
I can't hear you.
Increase?
Increase it. So that way I get the product I don't want.
You lower it because the activation energy is lower for our product.
Okay. So I lower it, and that way I get more efficient, I get less S relative to R. However, what happens to my conversion?
If you lower it, the temperature conversion drops
Because the rate goes down. So I'll get more R relative to S, but very little R and S overall because the rates go down. They go down exponentially with temperature. So I have a compromise situation. If I want to, if separation is expensive, then I want to maximize this thing. So if this is constant density, then I want to maximize CR out minus CR in, which is phi R over A, CA in minus CA out. Okay, well, let's, so we can just do that immediately. First I need to know what phi is, and again, let's do this for CSTR, where I have a single temperature. So what is phi here?
It is the rate of RA
What is
over
the
RD.
formula?
RA over R. I'm sorry, RR over RA,
which is equal to?
which is equal to K1 times CA divided by K1 times CA. Yeah. K1 plus K2 times CA.
Good. And which CA is this for CSTR? CA where?
CA the exit.
At the exit. So I have CA in minus CA, and to save myself some writing, CA without a subscript is CA out. But we have to write a little bit less. Okay, well, what I need to be able to do here is I need to write K1 as a function of temperature and CA out as a function of temperature. They're both functions of temperature. And of course K2. So I still have Ki is Ki0 e to the minus EI over RT. But now I also have to figure out CA out. What equation gives me CA out?
As a function of temperature?
Well, it's a function of tau, temperature.
The design equation?
Design equation, yes. So the design equation for CSTR says tau is equal to C in minus C out over minus RA out, which is CA in minus CA. Remember, when I don't put a subscript, I mean out. And KCA minus KCA is K1 plus K2 CA. And we've solved this 100 times in this class. CA over CA in is equal to 1 over 1 plus K1 plus K2 tau. Okay, so now I can plug everything into here and maximize. So, well, the first thing I can do is I can notice that the CA is canceled here. So I have a little less plugging in to do than it could have been. So I have CR out minus CR in is equal to. Again, you don't have to write that much. You can just photograph this at the end. Okay, that's equal to K1 over K1 plus K2 times CA, and I'm going to factor out a CA in, times 1 minus CA out, CA over CA, CA out over CA. So 1 minus this, and 1 minus this is just 1 plus K1 plus K2 tau minus 1 over this. So it's just K1 plus K2 tau over 1 plus K1 plus K2 tau. Okay, so this is what I need to maximize. So let's take ddt of CR out minus CR in and set it equal to 0. So that's CA in, and I have a denominator squared. And now I have the numerator. So the derivative of the numerator is K1, I have the product. So I've got K1 E1 over RT squared, K1 plus K2. I have a tau I can pull out. Plus K1 times K1 E1 over RT squared plus K2 E2 over RT squared times 1 plus K1 plus K2 tau minus FG prime. So I've got K1 A1 plus K2, I factor out the tau, times the derivative denominator, K1 E1 over RT squared plus K2 E2 over RT squared. Times 1 plus K1 plus K2 tau. Plus K1 plus K2 times the derivative of this, which is K1 E1 over RT squared plus K2 E2 over RT squared tau. And hopefully lots of stuff will cancel. Well, since this is equal to 0, I can get rid of this. And let's see what I have here. So I have so I've got K1 plus K2 tau. And I can just, I was factoring out a tau. So, actually, I factored out the tau from this term, but not from the other term. So, let's just make sure I put the tau in the right place. So I've got F prime. So let's put the taus back in. Plus this times derivative of this times this. Plus this times the derivative of this. Times the denominator. The denominator also has K1 plus K2. Plus minus FG prime. F times G prime. So F times this plus this plus okay. And let's make sure I don't remember it being this complicated. All right, let's see what we can do here. So there should be a bunch of stuff that cancels. Okay, so I have a 1 plus K1 plus K2 tau, K1 plus K2. 1 plus K1 plus K2 tau, K1 plus K2. Now, here it's multiplied by K1 tau, K1 E1 over RT squared. So K1 E1 over RT squared times K1 tau. K1 E1 over RT squared, K1 tau, times K1 plus K2 times this. So this term is the same as this term. So those cancel. And it looks like this term is also going to cancel. So I've got K1 tau, K1 plus K2, 1 plus K2 tau, K2 E2 over RT squared. It's like this term also cancels. Okay, so now, how about from here? Just anything in cancel. So this whole term and this whole term look like they canceled. I probably could have seen that earlier. Probably could have simplified this. Okay, you could have helped me. This canceled here. That's why it was. That's why that all canceled. Okay, yeah, that would have made life a lot easier. But I think we took care of that just now. So this whole term canceled this whole term. And now what's left? So I've got K1, let's see, I've got K1 E1 over RT squared, K1 E1 over RT squared, times K1 plus K2 tau, times K1 plus K2 tau, with the plus and with the minus. And I'm canceling too many things now. Okay, I'm going to do this again because I think I got lost in the algebra. So let's do it again. When we cancel this out, it should be easier. So I've got a CA in tau. And now I've got K1, 0, e to the minus E1 over RT squared. E to the minus, sorry, K1, E1 over RT squared. F prime, G minus FG prime, minus K1 times K1 E1 over RT squared plus K2 E2 over RT squared divided by the denominator squared. Okay, so I've got K10 E1, so K1, sorry, this is K1. K1, did I lose a tau? I've got this tau out here. So I'm going to put this tau back in. So I have a tau here, K1 tau, K1 tau, and down here I have another tau. F. Yeah. Okay. So let's see. I've got K1 E1 over RT squared, K1 E1 over RT squared times tau, K1 tau E1 over RT squared, K1 tau E1 over RT squared times K1 tau. So this term cancels this term. And the other term won't cancel because I've got an E1 and E2. This thing is equal to 0, so I can cancel this and I can cancel that. And what else can I cancel? 1 tau is going to cancel from each one, and K1 is going to cancel from each one. Then what am I left with? I'm left with E1 over RT plus E1 RT squared. Oh, and I can also cancel the RT squared. So here I have E1 times 1 plus K2 tau is equal to K2 tau E2. If I haven't made any mistakes, that looks like it might be reasonable. Okay, so this is E1 plus K2 E1 tau. And now I can bring this to the other side of the equation. I have E1 is equal to K2 tau times E2 minus E1. And this is equal to, so I have K2, which is K2 0, e to the minus E2 over RT, is equal to E1 over tau E2 minus E1. And now I can divide by K2 0. And take the logarithm. So I have minus E2 over RT is log of 1 over K2 0 tau E1 over E2 minus E1. So that tells me that 1 over tau T star is equal to R over E2 times log of K2 0 tau times E2 minus E1 over E1. Where I use the minus sign to flip the limits. I want you to check if this is right, given how many arithmetic mistakes I made along the way. That looks correct. Okay. So the top line I'm going to get rid of because that had algebra mistakes in it. Okay, so this is again the compromise temperature, because remember, if the temperature were too high, then if the temperature were too high, I'd be making S far more efficiently than R, so I wouldn't get enough R, if, even though I have a high conversion of A. If the temperature were too low, then I would get more efficient R production relative to S, but I get very little conversion of A because the rate of reaction would be slow. So here we have our compromised temperature. What would happen, on the other hand, if I had A goes to R goes to S? And let's say I was interested in R. Well, by the way, before I do that, if I look at this reaction, what we did is we calculated the optimum temperature for a CSTR, for a single CSTR, if we're stuck with one temperature. On the other, however, we may not be stuck with a single temperature. We sometimes may be allowed to have a temperature progression. For example, if we have CSTRs in series or a plug flow reactor. What sort of temperature progression would you suggest to try to get even more CR out or minus CR in? Volunteer? You see any sort of type of temperature progression that might do better than the single temperature in a single CSTR? Let's say I have N CSTRs in series. What would I do with the temperature progression there? And what would a motivation for N CSTRs in series be? Volunteer? Anybody awake today?
Recycle.
Listen to the question. Elephant. Your answer doesn't even, in the ball, it means you didn't listen to the question. You said a word that has, it's not just wrong, it has absolutely nothing to do with the question.
Each CSTR, you have an optimal temperature. If you put them in series, you get an optimal temperature for each individual CSTR because each of them will have a different conversion.
What sort of temperature progression might do better as far as producing R than having a single CSTR? First of all, why would we possibly prefer multiple CSTRs in series rather than a single CSTR?
Increase the concentration.
In what? Because CSTRs in series give you a higher concentration than just a single concentration, the single CSTR, which is always at the lowest concentration. So you get a higher conversion for CSTRs in series. So assuming I'm using CSTRs in series, which as Omar said is favorable for conversion, what type of temperature profile would I possibly try to use in that situation?
Lower the temperature is highest temperature for the CSTR.
Why is that? I want reasoning, not just an
Because
answer.
NCSTR is as you approach infinity,
That's
it's
not
like
the
a
question.
blood flow.
That's not the question. We already finished that. You answered that question before. Now I'm asking about the temperature progression. You're still stuck on the other question. I'm done with the other question.
So it decreases as more CSTR.
Temperature progression. Temperature progression. How many times do I have to say it? Temperature progression. We're talking about temperatures now.
For each CSTR, you have to have a higher temperature as the higher temperature, the higher answer.
But then I'll produce all S. I don't want S. I want R.
It progresses in that seesaw pattern. It goes up and it comes
Seesaw
back
pattern.
down.
Why is that?
So
Because the
it-
diagram looks nice?
Yeah, that's what the diagram
How
is.
about, remember, you want to get a promotion, not draw nice pictures.
Right.
I think we would first operate at low temperature because the concentration is higher, and then we would decrease the temperature for the next CSTRs. But if the order
Wait a minute, I start at low temperature and then I decrease the temperature?
no, you increase the temperature.
Why?
Because at first you have high concentrations, so if you take a low temperature, you would still get a production of R, even if it's slow, but it would be favorable for R instead of S. And then when the concentration goes down, then you would increase the temperature to have some reaction, even if it's less interesting.
That's correct. That's exactly the right reasoning. So we would start at low temperature because the concentration is high enough that I'll still get an appreciable rate, and then I want it to be efficient. And then once the concentration goes down, I've got nothing to lose because nothing's happening. So I raise the temperature to increase the rate of reaction. Even though it produces less efficient amounts of R relative to S, at least it produces something. Whereas at low temperature, low concentration, it will produce nothing. So a rising temperature profile would be better than a single constant temperature. Now if I go to reactions in series, we said what type of reactor does better for reactions in series? What's the better type of reactor?
A plug flow?
Plug flow reactor does better. And in fact, for a plug flow reactor, we found that the maximum that CR max over CA in, and this is if my inlet is pure A. If not, then I have a more complicated expression, and I may or may not have a maximum, was K1 over K2 the K2 over K2 minus K1. I'm sure that was more than 5 minutes ago, so probably most of you forgot this and didn't bother looking at your notes. But we have this as our maximum. If we're required to have a single temperature in the plug flow reactor, if we don't have a mechanism to vary the temperature of position, then how would I find the temperature to make this the largest? Back row? Can't hear you.
The graph.
The graph. Which magical graph are we talking about? Maybe if you listen to the question, you would say something, even if it weren't correct, that showed that you listened to the question. The question was, if I am stuck using a single temperature, and you're telling me to vary the temperature, it means you didn't listen to the question. How would I calculate the best temperature?
You have to take the derivative of CR max over CR.
I have to do what? Take the derivative with respect to and set it equal to 0. So I would take the derivative of this with respect to temperature and set it equal to 0. And I'm going to need this. Now, of course, we should look to see, here I have K1, here I have K2. One thing I can see immediately is if K1 is bigger than K2, then the higher the temperature, the better. It's not clear that this even has a maximum. If K1 is bigger than K2, then we know the higher the temperature, the faster this reaction will be compared with that reaction. If K2 is larger than K1, then this reaction is going to be faster than this reaction, so I'd want to go to low temperature. So it's likely that I either want to, that this may not even have a maximum. On the other hand, if you can check if it has a maximum. And if I'm interested in the production problem, then I would multiply that by, remember if I'm interested, well, this is CR max. Okay, in fact, okay, so I should step back. If I'm interested in the phi problem, capital Phi, to maximize that, R over A. Phi R over A is K1 CA minus K2 CR over K1 CA. This thing with temperature probably does not have a maximum, because the highest temperature, the higher the temperature, the faster this reaction will be with respect to this reaction. If K2 is bigger than K1, then I want to go to the lowest possible temperature in order to maximize phi. On the other hand, CR max over CA is the second type of question. So it's the question like this question. So even though going to high temperatures, if K1 is bigger than K2, we'll favor this reaction over this reaction. So even if, well, actually that's an easy one. If K1 is less than K2, then going to low temperatures will favor this reaction over this reaction, but will give me very little production. So in the case where if K1 is less than K2, then we expect this to have a maximum, because low temperature will favor this reaction over this reaction, but it will also give me very little production, like we had over there. So in this case, we expect there to be a maximum. On the other hand, if K1 is greater than K2, then the higher the temperature, the better, both for production, both for conversion of A and for production of R. So if K1 is greater than K2, we don't expect to see a maximum. Now again, let's say I have a temperature progression rather than a single temperature. What would you expect to be a good temperature progression here, or better than a single temperature? So this would be a compromise temperature if I had a single temperature. What if I had a temperature progression, if I had the electronics to do a temperature progression along my CSTR? What would you expect to be the best temperature progression? Let's look at the case K1 is less than K2. So what would I like to do here? What would be my optimal temperature progression here? With reasoning. I don't want just an answer. I want a reason.
It would be kind of parabola because it's
It would be what?
like
A parabola.
Like the temperature profile would start at a low temperature, increasing and go back to low.
Why? Okay.
Because at the beginning we have K1, we have a high concentration of K, right? So the lower temperature will favor the production of R.
Well, wait a second. Low temperature will favor production of R.
Yes. Because K1 is less than K2.
How can I produce S when I don't have any R?
Okay, after T equals 0, slightly after T equals 0, so the reaction.
So I have a tiny amount of R.
Right.
So the rate of reaction 2 is tiny because I hardly have any R.
You would want to start high to force A to R, but then decrease so that R doesn't form S.
Yeah. What we'd want to do, because these are reactions in series, as opposed to reactions in parallel, in the beginning I don't have to worry about reaction 2. There's no R. So let's just crank the temperature up to make the first to turn the whole system on. Remember, if you remember what those profiles look like, A looks like this, R looks like this. And S looks like this. So initially, around here, there's no R. I don't have to worry about this. So just go to a high temperature and make A get used up. It's only once I start getting around here, where I have a lot of R, that I have to worry about reaction 2. And then I better lower the temperature. And then just lower the temperature. And then the further on I go, I have little a and lots of R, I really want to have a low temperature. Because I have nothing to gain here. Very little A to make R, but a lot to lose, a lot of R to make S. So I want a falling temperature profile. Are there any questions?
Can you explain that what you had there with K1 less than K2?
Okay, the question was, when do we expect this to have a maximum? When do you have a maximum? When you have two trends that fight each other, right? Okay, so if K1 is bigger than K2, let's say not this case, the other case. If K1 is bigger than K2, then a high temperature is going to favor the first reaction over the second one, right? And a high temperature is also going to favor the rate the rates are going to go up. So clearly, I just want high temperature. There's nothing to discuss. On the other hand, if K1 is less than K2, then a high temperature is going to favor the second reaction over the first reaction. So that's bad. But a low temperature will favor the first reaction over the second. But if it's too low, I won't get any reaction at all. So too low a temperature, there's no reaction at all. Too high a reaction, all the reaction goes to S. So if I'm stuck with a single temperature, I need something in between. I expect a maximum. And that's why, in this case, I expect a maximum. Is that clear? Yes, no, maybe? Any other questions? Okay. If anyone wants to take a picture of the blackboard, do it now, because I'm going to erase. Okay. Up until this point, I'll start writing over here. Up until this point, we made a number of assumptions this semester. We started out with the assumptions of a single reaction. Single reaction. We also assumed single reactor at the very beginning of the semester. We also assumed that the reactions were isothermal. We assumed that the reactors were ideal, either zero mixing or infinite mixing. And we assumed single phase. And that's how we started the semester. The first thing we got rid of was single reactor. So early on, we got rid of this assumption. Then later on, we got rid of single reaction with selectivity. And in the most recent chapter, we got rid of isothermal. Now it's time to get rid of the next assumption, which is ideal reactors. So if you remember, with ideal reactors, we assumed that we either had perfect mixing, which we call CSTR, or zero mixing, which is a plug flow reactor. A recycle reactor assumes that I have a perfect plug flow reactor with a recycle. The reactor itself, though, is still perfectly plugged. So it's still an ideal reactor. Okay, so in real life, we know, just as we never have ideal gases in real life, we also never have ideal mixing. We always have some diffusion or some mixing, so it's never a perfect plug flow reactor. Yet we can never mix infinitely fast to get a CSTR. So what happens in real life? In real life, we have something in between, and we can try to design our reactors to approach one or the other extremes. And from the insight we've gained so far, we know which to try to approach. Now, sometimes the differences between the reality and the ideal cases are small. And sometimes they matter, sometimes they don't matter. On the other hand, sometimes they do matter. Sometimes, if we would like a CSTR behavior, so sometimes we would like a CSTR behavior. That means we would like the fluid in the reactor, or even an ideal plug flow reactor. We have a certain amount of time we want the reactants to spend in the reactor so that they can have enough chance to react. Well, sometimes you have stagnant regions in the reactor, like in what you think is a CSTR, and there's a whole part of the reactor where fluid just stays there forever and never quite gets mixed in the stream and never leaves the reactor. So that part of the reactor isn't really doing anything because I've got some fluid there that's already completely reacted, and it's just taking up space and not allowing new fluid to come in. So how do I know that? Similarly, I might have some part of the reactant that just takes a short circuit and goes right to the exit and never spends much time in the reactor at all. So that leaves the reactor unreacted. clearly those deviations from ideality are very important. So I can either have this short-circuiting or channeling, where the fluid just goes right from the entrance to the exit far too quickly. I could also have regions where fluid just circulates forever and never leaves. Okay, so how can I actually see if, well, first, how can I diagnose if this is a problem? And how can I correct? How can I design a reactor? So one is if I have an existing reactor, how can I diagnose to see if one of these problems exists? And the second question is, let's say I want to design a reactor and I know there are going to be some non-idealities. How do I know where they're going to be? How do I diagnose? How do I do my design? So I have two questions. How do I diagnose problems? And two, how do I do a design with non-idealities? Well, there's one obvious way to go. What I could do is I could take my system and do a detailed fluid mechanics model of that system. So I may have an impeller that's spinning, and I could try to solve for the fluid mechanics and mass transfer coupled to chemical reactions. So I could try to solve fluid mechanics coupled to mass transfer coupled to reaction kinetics. Typically the kinetics are nonlinear, and the fluid mechanics equations are nonlinear partial differential equations. Similarly for the mass transfer equations. Your geometry can be very complicated. So in complex geometry. And you may even have moving parts, because you have, typically in a CSTR, you have a stirring rod, some sort of stirrer. You can imagine that that's a difficult problem. And that might take you a few years to solve. You may not have a few years. Okay, well, and of course, historically, now we have big computers that can help. 30, 40 years ago, the computers were very slow, so this was a hopeless task. On the other hand, sometimes you might want to make the following simplification. Particularly with these sorts of problems, the ones I mentioned, channeling or stagnant regions, what's the issue in those problems? Is the issue the kinetics? Is the issue the kinetics? That is a yes or no answer.
No.
Is the issue the mass transfer? Is the issue the fluid mechanics? Okay, the issue is mainly what's the issue? Are the reactant is staying in the reactor way too long or not long enough? So if you notice, the issue there is how much time is each little droplet of reactant staying in the reactor. So instead of worrying about the detailed fluid mechanics, the detailed diffusion, advection, kinetics, the issue in those problems is stuff staying in the reactor the right amount of time or not? So if I want to simplify and only worry about simplify, is each fluid